Let's do a little thought experiment here. Let's say that we have a positive charge and it is moving to the left into this magnetic field on the page. So our magnetic field is represented by these X's. They indicate that the magnetic field is pointing into the page. Okay, now this positive charge is flying into this area of magnetic field and it's going to then experience a force, right? So if we use our right hand rule, the velocity is moving this way, or it's moving toward the left for me. Again, do it for yourself at home. It's moving to the left. The field is pointing into the page, and so that means that the force is going to be pointing down. See that? So if we have a magnetic force pulling this charge downward over here, then what's going to happen to the path of the charge? It's going to turn, right? So if this charge, once it enters the field, is now pulled downward like this, it's going to start to turn. Okay, and I'm going to draw this not as a smooth turn, but as a sudden turn. That's really not how it is, but it's going to be a little bit more clear for this diagram. Okay, so really it would curve, right? So now this velocity is more this direction. Okay, so if we use the right hand rule again, now my velocity is like this, and then my field is still pointing into the page. Now the force is not pointing straight down anymore, but it's pointing this direction. Okay, perpendicular. Remember that those three things, the field, the motion of the charge, and the force, are always perpendicular to each other. Okay, and so we have a force now pulling it this direction, right? And if there's a force pulling it in that direction, the path of the charge is going to change again. It's going to turn this way. Okay, and then we're going to just do the same thing over again. Do the right hand rule again, and you'll see that the force is going to pull in this direction, 90 degrees to it. And that means that the path of the charge is going to change. It's going to start moving this way and then this way until it's no longer inside the field. Okay, and so in our case over here, let's say that it exits the field like this. So the field has just turned it in a half circle and sent it back out the way that it came. Okay, so because the force and the velocity are always perpendicular to each other, we're always going to get the same type of motion when a charge enters a magnetic field. Okay, so for a charge moving in a magnetic field, the force and velocity are perpendicular, which results in circular motion. That's going to be our result. Let's look at this another way. We've got a charge that is moving in a circle inside a magnetic field. What direction is the force? So we can look at this two different ways. First of all, we know that if this charge is moving this direction, that means that the force must be pulling it perpendicular to its path, right? So its initial velocity was this direction, and so its force must be this direction in order to make it move in a circle. So here's our magnetic force. Okay, so that would cause it to move in a circle. That's really all it's asking us for in this case. But we could also determine whether it was a positive or a negative charge based on what it's doing. Okay, so this question already told us that it was a negative charge, but we didn't need to actually know that. We could have determined that ourselves. And so if we were using the right hand rule, if the velocity then was going upward and it was turning toward the center, so like this, that means the force is that way. That would mean that the field should be pointing toward you or out of the page. But it's not. It's pointing into the page. And so that means it must be a negative charge. We could try it with our left hand and maybe it would make more sense. So my fingers point into the page. My thumb is the velocity of the charge pointing upward, and the force is pointing inward like that. Okay? And so that actually fits. It fits our situation. So it must be a negative charge. So we didn't actually need to be told that. So it's important that you remember that the direction of the force on a moving charge is always going to be toward the center of a circle. And this means that that force can be called a centripetal force, right? Any force that's involved in moving an object in a circle is called a centripetal force. So you can probably see where we're going to go with this. We're going to put together a formula that combines this idea of magnetic force with centripetal force. So the formula for centripetal force, if you remember, is Fc for centripetal force equals mv squared over r. Mass of the object times its velocity squared divided by the radius of the circle. Okay, now we just said that in the case of a charge moving in a circle, the centripetal force is the magnetic force. And so we can just replace that Fc with Fb. So now Fb is mv squared over r. Okay, but we also have a formula for Fb now. Okay, and that's Q, V, B. And we're going to forget the sine theta for now, because that's only for when the field and the charge motion are not perpendicular to each other. And what we're working with here is only situations where they will be perpendicular to each other. So we don't need the sine theta for the motion of a charge in a magnetic field. QVB is equal to mv squared over r. Now we can cancel some things out and rearrange some things. So we have a v on both sides here, so we can get rid of the squared. We can get rid of one of the v's on the right side, and this one, if we divide both sides by v. And now we're going to rearrange this. So we have QB is equal to mv over r. And this is our formula that we're going to use to govern charges moving in a circle, but we're going to just write it like this. mv equals QB r. Okay, and this r is a big R, but that's only a convention. It's really just the little r from radius. Okay, and so just to make sure we know what we're talking about here, let's label this thing really quickly. There you go. Now I just want to point out one more thing. mv, mass times velocity. That's what's on the left side of this equation, mass times velocity. We know that as something else from earlier in our course as well. Mass times velocity is equal to momentum. So the momentum of a charge is equal to charge times field strength times the radius of the path it's following. That's just another interesting connection that may come up in your problem solving. And now for our example. A sodium ion has a +1 EC charge and a mass of 3.84 times 10 to the negative 26 kilograms. If the ion is traveling at 325 meters per second east into a magnetic field of 0.005 teslas up, determine the radius of the charge's motion. So, I've drawn this already over here, but I've drawn it as though you're looking down on this thing. Okay? And so the field is pointing upward toward you. So your bird's eye view, the field is pointing upward toward you. And this is showing you that this way is north, this way is south, etc. Okay? So the field is pointing up. Let's just keep that in your brain. We're supposed to figure out the radius of the charge's motion. So it doesn't tell us, it doesn't ask us which direction the charge is turning. It's either going to be clockwise or counterclockwise. That's not what it's asking us, but we're going to find that out as well, because in some of your problem solving, you're going to be asked for that. So let's just start with that. So we're going to use the right-hand rule to figure out what direction the force is, and that's the direction it's going to start curling in. So this is a positive charge, so that means I can use my normal right-hand rule. My thumb is pointing toward the east, my field is pointing upward, and so that means that my force should be pointing south. Force is south. Okay. So if my force is south, that means that my charge is going to start curling in this direction. Okay. And so my radius is going to be measured from here to wherever the center of the circle is, and my charge is curling clockwise. Okay, so some of the questions are going to ask you, is it turning clockwise or counterclockwise? You should be able to figure that out as well. So it's just asking us to solve for the radius. And in our circular motion formula, that's a big R. The radius is what? Okay, now this charge is in ECs. That's not going to work for us. We need it in coulombs. The mass is in kilograms. That's good. The velocity is in meters per second. And the field is in Teslas. So we're just going to go 1 EC is equal to 1.6 times 10 to the negative 19 coulombs. And so then we're going to go MV equals Q times B times R, and we're going to isolate the R. So I need to divide by Q and B. So MV over QB is equal to the radius. Now it gives me the mass, which is 3.84 times 10 to the negative 26 kilograms. It gives me the velocity, which is 325 meters per second. I need to divide that by the charge, which is 1.6 times 10 to the negative 19 coulombs. I also need to divide it by the field strength, which is 0.005 Teslas. And that will give me the radius of motion. Now when I do all that, I end up with a radius of 0.0156 meters.